We're doing chapter 24, and we're going to try to do, we'll do sections 3 and 4, and followed by chapter 25, section 1. So that's the plan. So the issue is I want to find, I have some xy axes, and I have some curve under the xy, so some curve over there, and I want to find the area underneath the curve. So that's what I want to do. So I've got some function f of x sitting right there, y is equal to f of x, and I want to find the area of the curve between a and b. So that's the plan. And back in the good old days when I had a calculator, what I could do is I could have my curve. I could find a delta x. So here's x1. There's x2. And delta x would be x1, x2 minus x1. So it's some small distance, and I'm going to go and I'm going to cut this guy up, and I'm going to come all the way out to where my b is. So each of these guys are equally spaced. I have a delta x between each one. That's what I have. So now if I go and take the summation of something, let's see, n equals 0 to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. There's 6. 1, 2, 3, maybe. And I take the function at x times delta x at each of these things. So I'm gonna go in and find out what the function is at that point, multiply it by delta x and get that area. And then I'm going to do it again and get that area. And then I'm going to do it again and get this area. And then I'm going to do it again and get that area. And so on. And then I could add them all together, and then I could find the area under the curve. Now, if I take this delta x guy and I send him to 0, I'm going to approach 0. I'm going to get closer and closer and closer to these things, and 100,000 of them, and 1,000,000 of them, and 2,000,000 of them, and 100,000,000 of them. I'm going to get closer and closer to the area under the curve is what I'm going to do. There's 2 rules to do that. One is Simpson's rule, which I don't see the author worried about. And the other one, I forget who he is, but whatever he is. And in your calculus class, you'll worry about that too. But it turns out that the area under this curve is going to be f, capital F at the b guy, so there's the b guy there, here's the a guy back here, minus f at the a guy, where f is the antiderivative of the function f. So if I take the integral of f of x with respect to x, and I integrate it between a and b, I come up with the antiderivative of f of x at b minus the antiderivative of f of x at a. And now there's no constant of integration because I have limits to my integral now. It's no longer an improper integral. It's now a proper integral. There's no constant of integration anymore because they went away. So I've got a, think of it as f of b plus c minus f of a plus c, and now the c's have gone away because I got a plus and minus, and they're no longer there. I don't have to worry about them. And that turns out to be the area under our curve. All right. So I got some function y is equal to 2x. Okay, so y is equal to 2x looks like that. Goes out to 2, goes up to 4, and the area under the curve is 1/2 the base times the height, which is 4. So the area is going to be 4. Okay, now I'm going to kind of come over here. I'm going to take the integral from 0 to 2 of 2x dx. what's the integral of 2x? X squared. X squared evaluated at 0 and 2. I evaluated at 2 squared minus 0 squared, which is 4. Oh, isn't that convenient? It's the right answer. How glorious. I will do it again. I got some function that looks like this. And I hit that spot there. Y is equal to x squared. Okay, so at 1, at minus 1, I'm at 1, and at minus 2, I'm up here at 4. Well, it didn't look like I hit the right spot. I'll do better over here. 2, I'm up there at 4, and I want the area under the curve. So the integral of x squared dx evaluated from 0 to 2 is going to be x cubed over 3 evaluated at 0 and 2, 8 over 2 minus 0 over 2 is going to be 4 again. So now I can get the area under weird curves because I can just take the integrals. All right, so now we're going to look at them. Let's see, what are we going to look at first? Number 1? Yeah, we'll look at number 1. So we'll look at number 1. I got y is equal to f of x. So that means my slope is 1. I want to go 0 to 2. So at 2 on 2, 1/2 the base times the height means this is going to have an area of 2 when I get done. So when I do my integral, x dx evaluated from 0 and 2, that's going to be x squared over 2 evaluated at 0 and 2. That's going to be 2 squared over 2 minus 0 squared over 2, also known as 2. I already knew it was 2 because I calculated it in my head beforehand just to make sure I didn't make a mistake. Okay, obviously this will be more convenient for something that is more difficult. Number 2, I have y is 5x, and I want the area between 1 and 4. Okay, so there's 1, there's 4. At 1 I'm going to be 5, and at 4 I'm going to be 20. So I want the area under that curve. So using my geometry thing, that's going to be, I got 20 here. 1/2 the base times the height there would be 1/2 15 times 3. So that would be 45 over 2 plus 20 would be 95 over 2. So we're thinking the area is 95 over 2. Integral 1 to 4 of 5x dx is going to be 5x squared over 2. Why do I do that? I increase the exponent by 1. I divide by the new exponent, evaluated at 1 and 4. So I've got 4 squared divided by 2 minus 1 squared divided by 2. And that's going to be 16. 16 divided by 2 is 8. 8 times 5 is 40. Minus 5 halves. Alright, so this would be 80 halves. So my 80 halves, that'd be 75 halves for a final answer. Why didn't I get 75 halves up here? Oh, I did get 75 halves. I just didn't write it right. No. This is 3 times 5, so this is going to be 15. And 15, I'd be 30 halves. 30 and 45 halves is 75 halves. So if I would have done that right, I would have known I had the right answer down there. Okay, good enough? Going fast enough? Number 3. Integral 1 to 3 of 2x squared dx. I could draw a picture, but it wouldn't do me any good. 2x cubed over 3 evaluated at 1 and 3. So I put the 3 in, 2, 3 cubed over 3 minus, I put the 1 in, 2, 1 cubed over 3. 27 divided by 3 is 9, times 2 is 18. 18 minus 2/3. Okay. Well, we'll just call it 17 1/3 and call it a day. Well, if it's 18 minus 2/3, I was going to change this to whatever it is thirds and subtract 2 from them, but why bother?
Yeah, gotcha.
Yeah. So I could make that an in fact, I'll do that on my calculator. I'll do it. 17 1/3 changed to an improper fraction. 52 thirds would also be a perfectly okay answer. And number 5? That was, no, 5.
Yeah, 5.
Y is equal to 3x squared minus 2x, and I'm going between 1 and 2. Integral between 1 and 2, 3x squared minus 2x dx equals x cubed minus x squared evaluated at 1 and 2. Alright, so I'm going to have 2 cubed minus 2 squared minus 1 cubed minus 1 squared. Well, I can do this one pretty easily. 8 minus 4 is 4, so the answer would be 4. Now, I can only do the integrals that I have rules to do the integrals for, right? So that basically means the power guy and a constant is the only thing I can do right now. And so someday maybe I can do more, but that's about all I can do right now. Number 7. Y is equal to 3 over x squared. And I'm going to go between 1 and 2. Okay, so I want the integral from 1 and 2 of 3x to the minus 2 dx. So that's going to be 3x to the minus 1 with a minus sign out in front, evaluated at 1 and 2. Okay, so I'm going to have minus 3 over x, evaluated at 1 and 2, minus 3 over 2 minus a minus 3 over 1. Okay, so I got minus 3 over 2 plus 3, which gives me a positive 3 over 2. Okay, now I'm not going to draw anything. I got to go all the way out to problem 23.
No, only to 11.
Oh, I'm looking at the wrong place.
I think so.
Okay, only to 11. That's no, only to 9.
No, 11, because it's Monday 19th.
Oh, Monday the 19th.
Yeah.
Oh, I see it. Okay, I see. I'm in the right spot now. All right, so I just did what? 7. So if I do 8 and 9, then I can go on.
9 and 11.
9 and 11. Okay, so number 9. Y is the square root of 3x minus 2. I'm going to go from 1 to 2. Okay, so I want the integral of 3x minus 2 to the 1/2 evaluated at 1 and 2. So the first thing I'm going to do is guess that my form is going to be 3x minus 2 to the 3 halves, and then g prime would be 3 halves 3x minus 2 to the 1 half times 3. So I need a 9 over 2 sitting there, which means I need a 2 over 9 sitting here. Okay, at that point I can solve the integral. 2 over 9, 3x minus 2 to the 3 halves evaluated at 1 and 2. 2 over 9, 3 times 2 minus 2 to the 3 halves, minus 3 times 1 minus 2 to the 3 halves, 2 over 9, 6 minus 2 is 4. The square root of 4 is 2. The cube of 2 is 8. Minus 3 minus 1 is minus 2 is 1. 1 raised to anything is 1. 1. So it looks like I've got 14 over 9 as my final answer. Number 11. Y is equal to 4x minus x cubed, and I'm going 0 to 2. Okay, so I want the integral 0 to 2, 4x minus x cubed dx. So that's going to be x squared over, no, 2x squared minus x to the 4th over 4, evaluated at 0 and 2. I like this one because when I evaluate it at 0, I get a 0 and I don't have to do much. So 2 squared is 4 times 2 is 8. 8 minus 2 to the 4th, which is 16, divided by 4, which is 4, and our final answer is 4. Okay, now on page 805, we have to deal with a theorem. I don't believe it. This is a tech math class. How would we do that? But the fundamental theorem of calculus. This was given to us by Newton, although he did wimp out and make us keep it secret until 50 years after his death. But he did tell us that the integral a to b of some function of x with respect to x is going to be the function, the antiderivative of that function at b minus the antiderivative at a. And that f prime, capital F prime of x, is f of x. So this turns out that capital F is the antiderivative of f of x, and that ends up being that way. That was a revolutionary type thing to come up with, for him to do that. Very nice of him. On page 807, we find that if we have an integral a to b of f of x dx, that that's going to be equal to minus the integral b to a f of x dx. So when I change my limits of integration, then I also get come up with a minus sign in front of it. Okay, we get to do problems up to 13. So we're looking at problem number 1. I want the integral of 0 to 1 of 5x dx. All right, so I got 5x squared over 2 evaluated at 0 and 1. When I put a 0 in, I'm going to get 0, so 5/2. Number 3. Integral 1 to 2 of x squared plus 3 dx. So I'm going to have 5x cubed over 3 plus 3x evaluated at 1 and 2. I put a 2 in and I get 8 over 3 plus 6 minus 1 over 3 plus 3. Oh, well, let's see. 8 over 3 plus 6 minus 10 over 3? 10 over 3. So that would be 5 1/3. Yeah, I think that'd be 5 1/3. Okay, number 5. Integral 2 to 0 x cubed plus 1 dx. All right, well, x to the 4th over 4 plus x evaluated at 2 and 0. Okay, so that's going to be 0 minus 2 to the 4th is 16 divided by 4 is 4 plus 2, so I'm going to be minus 6. Okay, number 7. Look, turn the page. It's getting boring yet? Pretty much. Well, maybe not. Integral minus 1 to 1 x squared plus x plus 2 dx. Alright, I'm going to have x cubed over 3 plus x squared over 2 plus 2x evaluated at minus 1 and 1. Alright, so I put the 1 in. 1/3 plus 1/2 plus 2 minus, I put the minus 1 in, minus 1/3 plus 1/2 minus 2. Okay, so 1/3 minus 1/3 minus a minus 1/3 would be 2/3. 1/2 minus 1/2, that goes away. 2 minus a minus 2 would be 4. 4 and 2/3. You notice that all we're doing is just requiring you to do 7th grade algebra over again, right? Now, why are we doing that? Why are we making you redo your adding and subtracting of fractional numbers?
Because we forgot how.
Yes, exactly. So the sole purpose of calculus is to review 7th grade math. Okay, that's the only reason it's in the curriculum. Haven't you figured that out yet? It's the only reason it's in the curriculum, because it's important that you can add fractions. And so now we just have another way to add fractions, make you do it, and and most of the time you don't even understand that that's what you're doing, you know. But that really is all there is to it. Number 9. You don't believe me, do you? Oh well, you'll believe sometime. Someday you'll push the I believe button. Doug Cordoville was right. Minus 4 to 9. Back to this area of the curve thingy. If I have something like this, and I go from 1 to 2, for example, well, I have as much under the curve on the positive side as I do on the negative side, so the end area of the curve is going to be 0. So anything below the 0 on the on the y-axis, those are all negative things, and everything above is positive.
So the problem would be 0.
Well, if this were the problem, if I had a curve that looked like that and I had as much above, so if I take a sine curve, for example, so I got this sine curve, blah, 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 and I want the integral of sine x from minus 90 degrees to plus 90 degrees, that's going to be 0. I have as much below the axis as I have above the axis. All right, back to the number 9 problem that we're trying to do. 3x to the 1/2 plus x to the minus 1/2 dx.
It's not a negative 4.
No, it is a positive 4, isn't it? First time I looked at it, it was clearly a negative 4. Who got out of their chair and marked my book when I wasn't looking? Put the white out on it. Somebody.
I didn't do it this time.
Joel did not do it this time, but I know he's done it in the past. All right.
Yes, I have.
All right, so that's 3x to the 3/2 divided by 3/2 plus minus plus x to the 1/2 divided by 1/2 evaluated at 4 and 9. All right, so I've got 2x to the 3/2 plus 2x to the 1/2 evaluated at 4 and 9. And it'd be nice if that looked more like a 4 than a squiggly thing there. All right, so I put in the 9. The square root of 9 is 3. 3 cubed is 27. 27 times 2 is 54. Minus 3 times 2 is 6. Minus. I put in the 4. I square root it, I get a 2. I cube it, I get an 8. Times 2 is 16. Minus. Square root of 4 is 2. 2 times 2 is 4. Okay, so I got this is a minus guy, so this is 12 minus 12. Okay, so that'd be 54 minus 18. Oh, what in the heck is that? 36? 36. All right. Number 11. We'll do number 11 and then we'll do number 26 and then we'll move on to the next section. Oh, we got to do 13?
Yeah, we still got to do 13.
Okay, got to do 13. All right. I figured by now you'd want to do 13 by yourself.
Oh, no, of course not.
Integral from 1 to 9 x plus 3 x to the 1/2 dx. Okay. Can I solve that? Do we have any method to solve that yet?
No.
Yes, we do, but not in that form. Integral 1 to 9 of x to the 3/2. This is minus a half, though, isn't it? It'd be nice if I wrote the problem down. 1/2 plus the integral 1 to 9 of 3x to the minus 1/2. Can I solve those guys now? Okay, I couldn't have solved them together. I don't have any method to do that. But if I separate them that way, then I can solve them. All right, so this is going to be x to the 3/2 divided by 3/2 evaluated at 1 and 9 plus 3x to the 1/2 divided by 1/2 evaluated at 1 and 9 Okay, I put in the 9. Well, I'll rewrite this. 2/3 x to the 3/2 halves, evaluated 1 and 9, plus 6x to the 1/2 evaluated at 1 and 9. All right, I didn't have to do that step. I could have probably got away without it. 2/3 times, that's 27. 27 minus 1 plus 6 times 3 minus 1. Well, this side is 12, so that would be good, as long as I didn't have an equal sign there. 26. 26 times 2. 52 over 3. 52 over 3 plus 12. Well, that was good. All right, calculator time. 52 over 3 plus 12 equals 29 1/3. Now, I'm sure I could have gotten that without my calculator. But was that 13?
That was 11.
That was 11. It took a whole page.
Yeah, 13's electrical. Electronics one.
It is? X to the 4th? How can 13 be electrical?
Oh, I'm on the wrong page. Never mind.
Thank you, Joel. Helping me out here. It's the integral 1 to 2. 1 to 2. We should do the summary problems. Is that what you're telling me? 3x plus 4 raised to the 4th. All right, now, there's many ways to do this problem, right? So we're going to do it with Pascal's triangle.
Excellent.
Dumbass idea.
I like putting it in the calculator. It works a lot better.
Yeah, we're going to use Pascal's triangle. And say that this is the integral from 1 to 2 of 3x to the 4th plus 4 times 3x squared times 4 plus 6 times 3x, that's cubed, 3x squared times 4 squared plus 4 times 3x times 4 cubed plus 4 to the 4th dx.
Why the hell did you ever do that?
Well, I guess we're not going to use Pascal's triangle because that's way too much work. All right, so we're going to do it again without Pascal's triangle. Well, I just wanted to show you that it could be done with Pascal's triangle.
It's just a lot of work.
3x plus 4 to the 4th dx. Now, we're going to guess that my antiderivative is in the form 3x plus 4 to the 5th. And then y prime is going to be 15 3x plus 4 to the 4th. So I need a 15 and I need a 1/15. Okay, now I'm all set. So this is going to be 1/15 of 3x plus 4 raised to the 5th evaluated at 1 and 2. All right, so Connor says that his calculator already has the right answer in it.
Yeah.
So as soon as I get to the problem being done, then he'll verify that I have the right answer. Isn't that cool of him?
He's special.
Isn't he special?
His calculator has an on it.
All right, so 2 times 3, that's 10. This is 10. 10 raised to the 5th power minus 7 raised to the 5th power. Well, how the heck am I going to do that? 1e5 minus 7 raised to the 5th equals, divided by 15 equals, and I got 5546.2. Is that what we got? Okay. See? Even Connor's calculator can work these problems. I mean, really. What can we say? Okay, so we're going to do 26 next, just to say we did. We don't have to do 26.
Let's go ahead. Oh, I'm out of paper.
26. So we have to stop the class. Joel's out of paper. By the time I get the thing written down, you probably have enough paper. And so I got integral 2 to 3. 2 to 3. 2x minus plus 1 divided by square root of x squared plus x minus 2 dx. Okay, so we're going to guess that we're going to be in the form x squared plus x minus 2 to the 1/2. And then the derivative of my guess is going to be 1/2 2x plus 1 to the minus 1/2. So I need a 1/2 here and a 2 there. 2x plus 1. And on the inside, I keep the inside. So I don't have enough room to write it unless I go small. X squared plus x minus 2. All right, so 1/2. I was right in what I was doing. 2 times x squared plus x minus 2 square root of, evaluated at 2 and 3. 2 times, okay, so 3 squared is 9. 9 plus 3 is 12, minus 2 is 10. So I got the square root of 10 minus 2 squared is 4, plus or minus 2, so that'd be the square root of 2, so that'd be square root of 4, which would be 2. I would go with 2 square root of 10 minus 4. But I'd be perfectly happy with a decimal number there too. But there's nothing wrong with that number. Okay, so now we're going to go to section 25.1. And what we're going to do, instead of finding the area under a curve, we're going to find the area between two curves. So this is f of x, and this is g of x, and we have some point here a, and we have some point b there, and we want to find the area between the curves. So we're going to take the integral a to b of f of x minus g of x dx, and now we're going to find the area between the two curves. Before, my g of x curve was y is equal to 0, and so everything above the x-axis was positive, everything below the x-axis is negative. Now I'm going to have a different curve to be the bottom part. Okay, so that's the theory. Area between the curves. And I could do it in a corner. I could do it on the y-axis too. I could have two curves, and one's like this, and the other one's like that. And now I'm integrating y between there and there. So I could have integral a to b f of y minus g of y dy. I could do that as well, find the area between those two curves. All right, so that's the plan. And I only have to do 3 problems, 1, 10, and 24. Now, obviously I'm doing 1 because that's easy. Obviously I'm doing 10 and 24 because the answer's on the back of the book and you can't tell me it's wrong. But Connor is sitting there with a calculator that could, in fact, come up with the answer. All right, so find the area bound by the following curves. All right, well, we've got to have a picture. All right, so y is x squared. That's this guy. Y is equal to x squared. And then x is equal to 1. X is equal to 1. And y is equal to 0. Y is equal to 0. So that'd be that curve there. And that makes this extremely easy. How come this is so easy? I don't know. Integral x squared dx between 0 and 1. From 0 to 1. Boom. X cubed over 3 evaluated at 0 and 1, also known as 1/3. Yeah, that was all right, I guess. Number 10. Y is equal to 2x squared, and y squared is equal to 4x. Okay? So y is equal to 2x squared is something that looks like this. When I go through 1 or minus 1, I'm at 2. Okay? This other guy looks like y is equal to 2 the square root of x. Now, the square root of x is going to be something that looks like this. And it looks like that. When x is 0, y is 0. When x is 1, y is 2. So we're looking at that area there. So the curve on top, so we're going to go integral 0 to 1 to the square root of x minus 2x squared dx. Because the square root of x curve is going to be on top of the 2x squared term. If you put it the other way, you're going to get the wrong answer. It would be a negative answer, which would give you an indication that how can I have negative area? I can't. I'm doing it wrong. Okay? So now I've got 2x to the 3 halves divided by 3 halves minus 2x cubed divided by 3 evaluated at 0 and 1. Okay, so I got 4x to the 3 halves divided by 3 minus 2x cubed divided by 3, evaluated at 0 and 1. At 0 I get 0, so that's good. At 1 I get 4/3 minus 2/3. Final answer, 2/3. And then I come back and look at my picture and yeah, I guess 2/3. He got 2/3. If Connor got 2/3, it must be right. Yeah. Now, I could, seeing that I'm not doing anything else, I could put it in maple and look at the curves themselves, because what do these curves look like? You know, that would be a reasonable thing to do. And to put it in there just to solve it, that wouldn't be reasonable. But to do it as a graphing thing, so we'll have a y, where's y? Y equals 2x squared. 2 times x squared. Oh, I'm not sure that's going to work. That should work. And then we'll add another one. Y squared equals 4 times x. Okay. We really don't have to go minus 5, right? So we can go 0 to 5. 0 to 5, and what is this guy going to be at 5? We don't really want to go to 5 either. We'll go to 2. 2, and 2 squared for 8, and we'll go up to 8. And do we have to worry about anything that's negative? Probably not. So we'll go 0 to 8 on that guy. And so there's my curve. How do I know which one's which? Well, this looks like a square root curve in green, and that looks like the squared curve there. So now that I have it drawn like that, going from 0 to 1, yeah, that looks like probably 2/3 sitting there. Maybe it looks like that. All right. What's next? 24. Number 24. Okay, so y is equal to x. Y is equal to x. Okay. Y is equal to x minus x plus 6. Okay, so y is equal to minus x plus 6. So I'm going to cross here at 6. I'm going to have a minus thing, so I'm going to cross over here at 6, and I'm going to look like that. Okay, so I'm going to have a minus 1 slope. I'm going to have a y-intercept of 6. And the third guy, y is equal to x over 2. Okay, so that means I have a slope of a half. Slope of a half coming down like that. Okay, so that being the case, I want to want the area. What color am I not using? I'm going to want the area in here. That's what I'm looking for. Okay, so I have I'm between this guy and that guy to that point, and then from here to there the other way. So I have to know that x1, and I have to know x2. All right. So if x is equal to minus x plus 6, and x is equal to 3. So this guy's 3, and if minus x plus 6 is equal to x over 2, then that means that 12 is equal to 3x, x is equal to 4. So that point there is that x is equal to 4. Okay, so without a curve, without a good drawing, I can't even set up the integrals. Okay, now with the integral set up, I'm going to have the integral from 0 to 3 of x minus x over 2, plus the integral from 3 to 4 of minus x minus plus 6 minus x over 2 dx dx. Okay. But until that point, Connor's calculator sucks, right? Now, he could have put in those curves and had these graphs drawn, and he could have moved his thing down to figure out where those points are. Oh, you don't even have that calculator. Oh, you got that remedial calculator. Okay. You just have a TI 36 Pro that does integrals. Well, that really does. That's very interesting, isn't it? All right, back to solving this equation so we can go home. X squared over 2 minus x squared over 4, evaluated at 0 and 3, plus what? This is going to be minus 3x squared, right? So that's going to be minus 3 over 2 x squared over 4 minus, no, x cubed over 3. Because it's x, it's minus 3 halves x. No, that's minus 3 halves x. Okay, right, minus 3 halves x. So I was right the first time. Where's the undo? Undo, there. That was right. Then I've got a plus 6, which becomes plus 6x, evaluated at 3 and 4. Okay, at 0 I'm going to be 0. 9 halves minus 9 quarters plus minus 3 halves 16 over 4 plus 24 minus a minus 27 over 6 plus 18. And it is getting a little bit late in the day. I'm not sure that that's right, but we'll go with it anyway. 9 halves minus 9 quarters minus 4 goes into there, minus 6 plus 24 plus 9 over 2 minus 18. Well, it's time to take out the calculator and see what it says. 9 halves minus 9 quarters minus 6 plus 24 plus 9 halves minus 18 equals 6 and 3 quarters. And that's clearly a, how am I going to believe that piece of crap, right? All right, so we'll come back into Maple and do an integral and plus another integral. And then we're going to have to remember what the integrals are. Okay, so this goes 0 to 3, 0 to 3, and 3 to 4. Well, at least I got that right.
Yeah.
All right, now I want x minus x over 2. Well, that's kind of silly to have x minus x over 2, but that's what we're going to put in. X minus x over 2. And the other guy is minus x plus 6 minus x over 2. Minus, is that a minus? X plus 6 minus x over 2. So it's minus x plus 6 minus x plus 6 close parentheses. And what do we want? We want 6 2/3. And if we don't get it, we're going to go home anyway. Is that the story? It's 0.
No, it's 3.
It's 3.
Yeah.
Where's the 3?
You got that first.
Oh, there's the 3.
You got
I see
that
the.
first.
No, it doesn't matter.
Huh?
Anyways, I got 3 on it.
So the answer's 3.
Yeah.
No, it's called they're wrong.
Oh, it can't be.
Calculators don't know what they're doing.
All right, so
No, I don't.
I got x minus x over 2 minus 6 minus x plus 6 minus x over 2, and the answer is 3. All right, so I gotta get a 3 out of this, and I've got that. Oh, bummer. All right, so where should I start erasing anyway?
Oh, we can just go.
All right, I've got that. I've got that. Okay, we'll start from here. And we'll start from there. That way I don't have to erase anything. Where'd it go? It went away?
You hit delete.
Way to go. Alright, so that's what I've got. So I've got integral 0 to 3 of x over 2 dx plus, I can't spell plus again, plus integral 3 to 4 of minus 3x over 2 plus 6 dx. Alright, so I've got x squared over 4 evaluated at 0 and 3 plus 3x squared over 4 plus 6x, this is a minus sign, evaluated at 3 and 4. So I got 9 over 4 plus, okay, 4 goes into there, square it. I've got a minus 3 over 4 plus 24 minus, I put a 3 in there, minus 27 over 4 plus 18. All right, take my calculator out. 9 over 4 minus 3 over 4 plus 24 plus 27 over 4 minus 18 equals 3. I got it. Okay, perfect. Sure, I'm glad I got that one right. Okay, any questions? All right, if not, we'll do a Control Shift